We're going to continue our introduction to logarithms, and now we're going to focus on solving some logarithmic equations. Before we do that, I want to remind you of a few facts from the previous lesson. Recall that our translator says that y equals log base a of x if and only if x equals a to the y. Not only does this describe what a logarithm is, but we can actually use this property to help us solve certain equations. Secondly, remember that logarithmic functions are one-to-one. They are the inverses of exponential functions. Exponential functions are one-to-one. Logarithmic functions are one-to-one. And the last thing I want you to remember is that the domain of a logarithmic function is 0 to infinity. So you can only have positive inputs to a logarithmic function. That doesn't mean that the variable has to be positive, but the input to the logarithm has to be positive. And the reason for this is that the range of an exponential function is only positive numbers, so the domain of its inverse consists of positive numbers. We're going to use one or more of these facts as we solve the following equations. Here's our first example. Let's solve the equation natural log of 3x minus 7 equals the natural log of x plus 9. Here we're going to use the fact that logarithms are one-to-one. Because logarithmic functions are one-to-one, when the outputs are equal, the inputs must be equal, assuming you have the same base on both sides. These are both natural logs, so they're both base e. The only way these two expressions could be equal is if their inputs were equal. Well, that means that 3x minus 7 must be equal to x plus 9. We didn't divide by anything there. We certainly didn't divide by ln, which is the name of the function. You can't divide by the name of the function. I better not catch any of you dividing by the letters ln. That doesn't make any sense. We're using the fact that these functions are one-to-one to set the inputs equal to one another. And then from here you subtract x from both sides, you add 7 to both sides, and we get x equals 8. And now we have to make sure that this is actually an allowable input to the original function. I know 8 is positive, but that's not the restriction. The restriction is that the input to the logarithm has to be positive. If I plug 8 back in for x, I get 3 times 8, which is 24. 24 minus 7 is 17. That number is positive and we're okay. We also get 17 as the input on the right side. So this really is an allowable input and it is a solution. Let's try a similar example. This says the common log of x squared equals the common log of negative 6x. The base here is 10. These two bases are the same. And because the bases are the same, the only way these two logarithms could be equal to each other is if the inputs were equal. So we get x squared equals negative 6x. This is quadratic, so we'd usually get 0 on one side. X squared plus 6x equals 0. We factor out an x. We get x times x plus 6 equals 0. And so we get two proposed solutions, x equals 0 or x equals negative 6. Now we check to see if these are allowable inputs to the original function. When you go to plug 0 in here, you get the log of 0, which we know is undefined. 0 is not an allowable input. So x equals 0 isn't actually a solution to this equation. You might also try to discount negative 6, but remember the restriction isn't that the variable is not allowed to be negative. It's that the input to the logarithm is not allowed to be negative. And when you plug negative 6 in for x, we wind up squaring that before it gets applied to the logarithm. Negative 6 squared is positive 36. That's okay. Over here we take negative 6 times negative 6, also positive 36. Negative 6 is okay. 0 is not, because you can't find the common log of 0. Okay, these examples that use the one-to-one property are pretty straightforward. When the bases are the same, you set the inputs equal to one another. Let's try a couple that use that translator. This says solve log base 2 of 5x plus 1 equals 4 for x. Here we don't have logarithms on both sides, so I can't just set 5x plus 1 equal to 4. And you cannot divide by the name of the function. Please don't try to cancel out the log. You can't divide by the name of a function. Instead, we're going to use our translator. Remember that we said that y equals log base a of x if and only if x equals a to the y. Let's rewrite this equation in its exponential form. The input to the logarithm goes by itself on one side. The input to our logarithm is 5x plus 1. I'm going to isolate that on one side. The base of the logarithm becomes the base of the exponential expression. The base of our logarithm is 2. That's the base of the exponential expression. The output of the logarithm becomes the exponent. The output of the logarithm is 4. So we get an exponent of 4. 2 to the 4th is a number we can calculate. 2 times 2 times 2 times 2 is 16. So this is just a linear equation. 5x plus 1 equals 16. so 5x equals 15, so x equals 3. Now we double check that 3 is really an allowable input, and yeah, of course it is. Plugging 3 in is going to give us 16. That's okay. Log base 2 of 16 really is 4, and there's our solution, x equals 3. Let's try another one like that. This says log base 36 of x squared minus 5x equals 1/2. I want you to pause the video and see if you can rewrite this in its exponential form. As a reminder, y equals log base a of x if and only if x equals a to the y. The input to the logarithm goes by itself on one side. The base of the logarithm is the base of the exponential expression. The output of the logarithm is the exponent. 36 to the 1/2, it means the principal square root of 36, which is 6. So this is x squared minus 5x equals 6. This is quadratic, so you'd want 0 on one side. This one happens to factor. This is x plus 1, x minus 6. And so we get two proposed solutions, x equals -1 or x equals 6. Before you discount x equals -1, let's check and make sure. -1 squared is 1. -5 times -1 is +5, and 1 plus 5 is 6. That's okay. Plug in 6. 6 squared is 36. 5 times 6 is 30. 36 minus 30 is also 6. These are both allowable inputs, and therefore both solutions. Don't discount a solution just because it's negative, or even because it's 0. That's not the restriction. The restriction is that the input to the logarithm has to be positive, not that the variable itself has to be positive. This example says the common log of x equals -3. Remember, the common log is base 10, so you might want to write this as log base 10 of x as a reminder. Rewrite that in its exponential form, please. When you rewrite this in its exponential form, you get x equals 10 to the -3, and we essentially have the solution. We would just usually simplify 10 to the -3. That means 1 over 10 cubed, which is 1 over 1,000. Let's try one more logarithmic equation like that. The natural log of 2x plus 7 equals 3. Rewrite this in its exponential form, please. The base of the natural log is e. So when we rewrite this, we get 2x plus 7 equals e cubed. Now, e cubed is an irrational number. We could come up with a decimal approximation for it, but we're not looking for an approximation here. It says solve for x. We want the exact solution. So just leave this as e cubed and solve this equation like you would any other equation. Pretend like that e cubed is an integer, like 10. What would you do first? Well, you'd subtract 7. You want to do the same thing here. Again, pretend like that right side is an integer. What would you do to solve for x? You'd divide by 2. Do the same thing here. X equals e cubed minus 7 all divided by 2. Let's do one more example with the translator, but this one's not a logarithmic equation. We're going to solve e to the 3x equals 10. Again, not logarithmic, but we can still use the translator to solve this. One more time, let me write out the translator. Y equals log base a of x if and only if x equals a to the y power. We're just going to go from the exponential form to the logarithmic form. The exponent is the expression that goes by itself on one side, so I'm going to isolate the 3x on one side. The base of the exponential expression becomes the base of the logarithm. Well, when the base is e, we usually write ln instead of writing log base e. It's not wrong to write log base e, we just typically write ln. The output of the exponential expression becomes the input to the logarithm, so we're going to plug 10 into the natural log. So this is 3x equals the natural log of 10. Dividing both sides by 3, we get the natural log of 10 divided by 3. Notice that it's not the natural log of 10/3. We're not dividing 10 by 3. We're dividing the natural log of 10 by 3. This is an order of operations issue. First, the 10 gets plugged into the logarithm, and only after we evaluate that do we divide by 3. So don't write this as the natural log of 10/3. That's a different number. This being an exponential equation, there are no domain restrictions. We're okay here. I want to solve a couple more of these exponential style equations, but we're going to do it in the context of word problems, talking about applications that we've discussed before. The first one we're going to look at is continuously compounded interest. Suppose $10,000 is invested at 6% interest compounded continuously. How long would it take for the investment to grow to a balance of $35,000, round to the nearest tenth of a year? Because the interest is compounded continuously, we're going to use that PERT formula, A equals P times E to the RT power. This problem is different than any other compound interest problem we've done before because the question isn't about the money, this time it's about the time. The time is the unknown. We know A, it's $35,000, that's the ending balance, and we know P, it's $10,000. E is not a variable, don't list that. R is given, it's 6%, we're going to represent that by 0.06, and the question is the time. So plugging all these numbers into the formula, we get 35,000 equals 10,000 e to the 0.06 times t, and the variable we're solving for is in the exponent. We haven't seen a compound interest problem like this. We're always solving for either a or p. But now we have the tools to do this. Let me copy this equation onto the next slide. We saw how to handle this in this generic example here. If we can isolate the exponential expression so that it has no coefficient to the left of it, then we can use the translator to rewrite it in logarithmic form. In our example, we do have a coefficient. There's a 10,000 in the way. Let's divide by that first. 35,000 divided by 10,000 is 3.5. On the right side, the coefficient cancels away. And now we have the format that we need in order to use the translator. See if you can rewrite this in its logarithmic form. The input to the exponential expression, the exponent, goes by itself on one side. The base of the exponential expression becomes the base of the logarithm. When the base of a logarithm is e, we denote it by ln, the natural log. The output of the exponential expression is the input to the logarithm, so the natural log of 3.5. To solve for t, we divide by 0.06. You're dividing the entire logarithm by 0.06, not the 3.5. This is t equals the natural log of 3.5 divided by 0.06. That is the exact amount of time it would take. We were asked to round this to the nearest tenth of a year, so we're going to put this into the calculator. The natural log button is 2 above the on key, ln. 3.5, then make sure to close the parentheses on that input so that you're dividing the natural log of 3.5 by the rate and not just the 3.5. We're going to divide that by 0.06. It comes out to about 20.9 years if we round to the nearest tenth. 20.9 years in order for $10,000 to grow to $35,000. One more example. This is a real-world example from science about radioactive decay. A radioactive substance decays exponentially at the rate of 0.0121% per year. So it decays very slowly. Suppose 50 grams of the substance is present in a sample. How many years will it take for the amount to decrease to 25 grams, round to the nearest year? We know that our model for exponential growth and decay is Q equals Q sub 0 e to the RT. So Q is the amount that we end with, and it's decreasing down to 25 grams at the end. So that's the ending amount of this substance. We're beginning with 50 grams, so Q sub 0 is 50. R needs to be converted to a decimal, so we're going to move that decimal point 2 places to the left and get 0.000121. And also remember, this is a decay model, so R needs to be negative. T is the time, and that's the question. How many years will it take? We don't know. 25 equals 50 e to the negative 0.000121 t. Now we're going to solve that for t. We know we want to use that translator to get this in a logarithmic form, but remember that we can't have this coefficient in the way. When you look at the translator, there's no coefficient in front of the logarithm. We need to move that first. So our first job is to get rid of the 50. See if you can do that. We move the 50 through division. We divide both sides by 50. So the left side becomes 1/2 or 0.5. Now we rewrite this in its logarithmic form. See if you can do that. The exponent goes by itself on one side. The base of the logarithm is e, so this is the natural log. The output of the exponential expression becomes the input to the logarithm. That's 0.5. Now we solve for t, and we solve for t by dividing by the coefficient on t, negative 0.000121. And so t is the natural log of 0.5 divided by negative 0.000121. We're asked to round this to the nearest year, so let's go to the calculator. Natural log of 1/2 or 0.5, close the parentheses, divided by negative 0.000121. So rounding to the nearest year, we get 5,728. This substance decays away so slowly that 50 grams would reduce to 25 grams in just over 5,700 years. So we've got a good sample of different types of logarithmic and exponential equations that we can solve now. We're still not ready for everything. We're going to have to pick up a little bit more about logarithms to solve other kinds of equations. But we're off to a good start. If you have questions about any of these examples or any examples you're trying in a textbook, let me know. We can talk to each other during an office hour, or we can send emails.